Hello, geometry friends. This is the last part of that problem we've been working on for days. But I'm going to do the problem and solution all in one video. I would highly encourage you to stop after the statement of the problem and solve it yourself because that's how we learn, right? Okay, a brief review. We found our two form. We have our Riemannian manifold with these, it's been parameterized like this. We found our wedge products, okay? Now, we still have these unsolved. So we need to solve these the products. So that's what part A is. Solve the above the three equations using these parameters to get on this side of the equal sign everything in U's and V's. Okay? So you solve these equations to get everything in U's and V's. All right. Part B, step 2. Substitute these three equations back into our two form. Now look at our two form. It's got X's, Y's, and Z's everywhere, right? So when you're done, your two form should be a function of U and V. So everything over here are U's and V's. All right, part C. Now we want to integrate our two form. I just said 0 to 1, 0 to 1 for U and V. And where you're going to get an answer. And you're going to get a scalar. And you're going to say, what does that mean? What's that scalar for? All right. So that's it, part A, B, and C. So stop the video and give her a whirl. Okay, you're back. Excellent. Solution, part A. Solve the three above equations. That was those. All right, so let's do number one. So here is dx wedge dy. Here's what you got. So we just want to take these derivatives, right? So x over u is 1, y over v is 1. That's 0, that's 0. du wedge dv. So there's dx wedge dy is just du wedge dv. The next one was dy wedge dz. Okay, so that's 0. Doesn't matter what the rest of them are. Y over v is 1. Partial z with respect to u is 2u, but we've got a negative. So here's our answer. One more. dz wedge dx. That's 0, so it doesn't matter. Partial z, partial y is 2y, but we got a negative. X over u is 1, so here's the answer. Now we put all of those back into our 2 form, but now remember you've got an x here, y there, and a z there. You got to put all that in too, right? So here's x, here's dy wedge dz, here's y, here's dz wedge dx, here's z, and here's dx wedge dy. Okay, we simplify, we factor out a du wedge dv, and we get this. Okay, part C, integrate it. So integrate minus u squared minus v squared from 0 to 1 of du dv. And even I could do that. And you get negative 2/3. And you go, what negative 2/3 what? What is it? Okay, in order to kind of tie this together with, I think we all have similar backgrounds. Let's solve this problem the way we learned to in vector calculus, okay? Because we learned how to do flux integrals in vector calculus, because that's what we just did. Okay, we take some vector, the field, and there should be a y, z in there. I always make a mistake. I can read this 27 times. That should be a f, y, and z. Okay, here's our manifold. Oh, look, I did it right. Here's our vector field. We put in our parameters, and we get this, right? And then we would take the partial derivative of that to find our basis vectors. So this is the partial of f with respect to u, partial f with respect to v. All right. So then the way it was defined for us was the dot product of the vector field with the normal would give the flux integral over the surface. Remember? Now, how did we find the normal? Well, it was the cross product of the basis vectors. So it's just that. You get this answer. Now we can write the whole thing out. We need to take this dot product. We do that, make a dot product, and we get this. We simplify, and we get obviously the same answer. So now we can integrate that exactly the way we did above, and we get this exact same answer, right? So I asked Google AI to make me a drawing of what I just explained here, and it did a really, really good job in less than a second. It's unbelievable. Okay, so here's our manifold. Okay, here's our domain 0 to 1, 0 to 1. Okay, that's our domain. Now, that on this surface, they call a surface patch. Okay, and we integrated that and we got this answer of negative 2/3. The normal, you see, because we did EU cross EV, the normal is pointing straight up. So this means that our result is in the opposite direction. So it is the net flow of 2/3 units, whatever the units are, in the direction opposite of the induced normal. Okay, so that's what we just did meant. And the connection between these things is in vector calculus, you're calculating the oriented manifold's tangent space using vectors to the cotangent space using differential forms. And what connects these two things together is the Hodge-Star operator. All right, so that was the entire point of the problem, was to show this. And I thought that was a good problem. I really learned a lot. I hope you did too. All right, see you next time.